Hey, welcome to math. Today we're going to look at lesson 24. So we are going to transition from rearranging, slope-intercept form, standard form, graphing, just one line, and get into systems. So from lessons 24 through the end of the module, up to 30, systems is our baby. This is what we're going to be looking at, what we're going to be referring to, also known as simultaneous, meaning same time, equations. Okay, so you should have these notes open on your iPad and you can follow along as we fill them in. Now, our goal for today really is just an introduction. I can introduce myself to systems of equations. Tomorrow in lesson 25 is when we'll actually start solving. We're going to solve on a graph. But for today, just an introduction to kind of help us start to see what a system would look like. So I'm going to continue to teach through this lesson, pause a couple times for practice, and then you'll be on your own to practice as well. Now, we're probably familiar with a weather system. We know that weather can happen simultaneously, like it can be sunny and windy, that would be a system, or it can be cold and rainy, or in this case, snowy and cold. So there's two different variables, right? There's the snow and there's the cold, or there's the sun and there's the wind. Weather sometimes has many variables, like it can be dark, cold, rainy, and windy. Like that would be a lot of things happening simultaneously. So there's weather systems, we're probably familiar with that. We also have airline systems. If you remember in our project we're looking at, it talks about flight patterns. So this is a map of an airline system, flights going from like JFK out to Dublin, out to Brussels, out to all over different parts of the world. So this would be an airline system, many lines happening at the same time. And then let's just brainstorm a second. What are some places you or your friends have flown to? I've never flown to New York City from Philadelphia, but I know it's possible. It's a very short flight. But I have flown to Tokyo, Japan. I've flown to Vienna, Austria. I have flown to where else have I been? To Dublin, Ireland. But then stateside, I've flown to North Carolina, to Florida, to Georgia. I've flown to California, I've flown to Texas. So flights, travel, we're familiar. We know that we are not the only plane in the sky when we're flying. So some cool places you've probably visited. You can write a few of those in. Now, what about a nervous system that's right within the body? A bodily system that in vertebrates is made up of the brain, spinal cord, nerves, ganglia, and part of the receptor organs. So we have this system, right? Even if you look at like the veins in your arm or in your skin, you know that there's more than one thing going on in there, at least I hope so. Now, let's just collect those thoughts. It says, systems are part of our world all around us. They maintain order. They can be used to locate specific things, like an address can help you locate your home. If you want to know where Broad and Chestnut intersect, you know where to find that on a map. Same's true for the system. Now, I like these pictures because it's going to kind of give us some insight into solving. You're going to either have no solution, which we've seen already back in lesson 7. Please go revisit lesson 4.7. One solution, meaning there's just one ordered pair, one answer, or infinite solutions, which is the same line. So no solution, one solution, or infinite. Just like when you solve an equation itself, it can have no solution, one, or infinite. When you solve a system, it can have no solution, one solution, or infinite solutions. And a solution, remember, is an ordered pair, not just an x value like we saw in 4.7. It's actually going to be the full coordinate, x and y. Okay, so let's look at this problem. Here it says, and I got some pictures because I didn't know if you were familiar with what these different items would be, but we got a magnolia tree. This is a picture of a pear seed and then a pear tree. And these pictures will make more sense here once you read the problem. This problem says, Polly planted a magnolia tree in her front yard. When she planted the tree, it was 4 feet tall. At the end of each year, she measured the height of the tree. Below is a table of data she collected. Use the table to create a linear graph of the data. So let me highlight some important information. It was 4 feet tall at the end of each year, below the table. And then the question actually tells me to create a graph. Now I could generate the equation, but because these are ordered pairs, like this will be 0, 4. Let's make that a little thinner. This will be 1, 6. This will be 2, 8. This will be 3, 10. And then 12. Oops, 4, 12. Makes it very easy to graph. So let's just go plot that in real fast. The dots. Great. Done. Created a graph from a table. Hopefully feels pretty easy. But Ms. Harkness, this is not new content. No, it's not. But we haven't even gotten to the pear tree part yet. Part B. On the same day, actually I like red for my answers. Let's go with green. On the same day as she planted that magnolia tree, of the magnolia tree, she also planted a pear tree seed. And remember, the magnolia tree was already 4 feet tall. This day she plants a seed. The equation below, represents how fast a pear tree is expected to grow each year. X represents years, which is always time, we know that. And Y represents the height in feet. Y is always our total distance. In this case, distance is a height. So now we have this equation, Y equals 4x. Graph on the graph to the right. Remember, we have our slope is 4, and then our initial value here is actually 0 because it's a seed. There isn't any initial height. And don't get all caught up in the fact that the seed itself has measurement to it. Yes, that seed has mass, but the tree does not have height yet. All right, so 0, right? 0, 0. So if we're 1 year in, 4 times 1, 4. If we're 2 years in, 4 times 2 is 8. You probably catch the drift, or you can just count rise over run, up 4 over 1, up 4 over 1. Because the slope was 4, remember? Cool, there's the pear tree. Now let me just compare both of them for a second. Hopefully you can see which of the trees has a steeper line, but if not, that's okay. We'll get to that. All right, so we have the magnolia tree growing, looks like 2 feet a year, right? 8 to 10, 2 feet a year. And then we have this pear tree, which we know is growing 4 feet every year. Part C. Using the information you have on the magnolia tree and the pear tree, answer the questions below. All right, so I want you to pause the video and go ahead and answer these questions either by yourself or with somebody. Take 2 minutes. All right, before I show you these answers, I want to make sure that you knew how to get the rate from the graph distance over time. And actually, for the magnolia tree, if you wanted to, you could pull 2 points and use the slope formula as well. And then we already discussed in part B because it's part of the equation. So here's what we came up with, that the unit rate for the magnolia tree is 2 feet per year. The unit rate for the pear tree is 4, so which tree grows faster would be the pear tree. You probably did not even need 2 minutes to figure that out. Now this next question in part C says, draw both of your graphs onto the graph, circle the point at which the 2 graphs intersect. Now since a magnolia tree has pink flowers, I'm going to draw in pink, and I got to start at 4 and then go up 2 over 1. So this pink is my magnolia tree. So in 5 years, it's going to be 14 feet tall. And then a pear is green, so let's go with my Kelly green. The pear started from a seed, but it's going 4 feet every year. Yep, there and there. Draw both of your graphs onto the graph. Circle. Circle. Doesn't say bold. Doesn't say highlight. Circle. So I'm going to do what the question wants me to do. I'm going to circle that point. What does the point represent? What do you think? Let's compare it. So it's at 2, 8, where 2 is what? Years. And 8 is what? Height. So what do you think it represents? That maybe 2 years into this project, both trees are 8 feet tall? You're correct. Let's write that in. So this is what we came up with. At the 2-year mark, both trees are equal in height. We know that the pear tree is growing faster, but it started smaller. And then we know that the magnolia tree started taller, it was 4 feet, but it's actually growing at a slower rate. So up until year 2, the magnolia tree is going to be taller, but from year 2 on, the pear tree will always be taller. Something valuable to know, comparing systems, rates, right? It's one thing to be faster, but if your initial value was greater or smaller, ultimately your graph will show you the actual trend. Okay, so I want you guys to work on this exercise 2. It's a little bit harder because you have to create your own equations, you have to graph them, and then find the point of intersection on your graph and say what it means. And then D says verify your ordered pair is the same. Verify that it is a solution. What does verify mean? It means you're going to take that coordinate, that x and y value where they cross, like if it's at like 4, 9, and you're going to put 4, 9 into the Denny's equation, and you're going to put 4, 9 into the IHOP equation. And mathematically, if your equations are correct, it will work for both of them. Okay, so you're probably going to need 10, 15 minutes to work on that.